presentation is going to be made by two presenters. So it's going to be Shufkan and Jeremy O. And the presentation is entitled Smart Data-Driven Building Management Framework and Demonstration.
First. Yes.
Hello, ladies and gentlemen. I'm Jeremy Ho, representing a team of engineers from Hong Kong's Electrical and Mechanical Service Department and the research team from the Hong Kong Polytechnic University. And we are happy to present today the Smart Data-Driven Building Management Framework and Demonstration. Our paper presentation today focuses on 4 parts. First, background and introductions, framework and methodology, case study, and then lastly, the conclusion. Climate change is a global issue, and in Hong Kong, we have targets to reduce the carbon emission from building sector by 60% by 2050. And to achieve this target, our government introduced the carbon neutrality target and the Climate Action Plan 2055. We aim to reduce the commercial building electricity by 30 to 40% by 2055. We also introduced the Hong Kong Smart City blueprint to have a green, intelligent buildings and energy efficient to create a smart environment. Reducing the electricity consumption in commercial buildings relies on the effective building management systems. However, integration in these areas include different difficulties. Firstly, the information gaps throughout the building life cycles limits the access to a complete status on the systems and equipment, as the building may have go through the multiple operators, clients, users, and the renovations. Secondly, reliance on a conventional control restrict the energy saving opportunity. Moreover, apply AI algorithms for buildings energy management also poses difficulty due to the need for standardizations of methodologies and the formats across the projects. To address this challenge in the AI-powered building energy environment, firstly, we propose eliminating the information gap by connecting and aligning real-time data on all systems and equipment present in a 3D zero change format. Secondly, AI implementation goes beyond conventional control. Further optimization can be achieved through the strategies such as predictive maintenance and the load predictions to achieve more energy saving. Lastly, our solution utilizes the standardized data integration schema to enable AI applications throughout different buildings. Now, I will hand over the floor to my research partner to present more details.
Okay, thank you for Jeremy's presentation. And my name is Xu Kan from the Hong Kong Polytechnic University. And my part, I will introduce the whole framework to all of you. And we can see that our whole framework contains 1, 2, 3, 4, 5 parts for multi-source data, the database, the semantic data integration schema, the AI engine, and the smart 3D interactive building management platforms. So let's start from the data from the buildings. Actually, in the whole life cycle of the buildings, we have different kinds of data. For example, from the design stage of the buildings, we have the static or the spatial information from the 2D drawings or the BIM models. And in the operation stage of the buildings, we have the operation data or the temporal data from the building automation systems or the IoT sensors. And this data would be extracted and stored in the database with the guide of the semantic model, the brick model. This is a kind of standardized building metadata description. And with this kind of semantic data schema, with the AI engine can query the data they want in a standardized way. And in this way, we can realize reduce the cost of the AI application development and deployment. So the AI engine would get the data and using to train the models and get the optimization result. This result would store in the database, and also with the real-time data with the real visualization in digital twin. And in this platform, as a cross platform, we can use the HoloLens mixed reality to see the data and help the operators for maintenance. And also we can deploy this platform in the Windows platform. And also we do a test and deploy this platform in our PonyU chiller plant. And this is the schematic diagrams of the chiller plant. We can see that we have 6 water core chiller and 2 air core chillers and 6 cooling towers and several different water pumps. And first, we extract the 3D models from the BIM model and develop the digital twin of our chiller plant. And also, we connect the real-time data in this digital twin to realize the real-time data visualization. Right side is the semantic model of this chiller plant. The points are for the entities in the chiller plant. For example, the chillers or the sensor point, and the line between the different points means the relationship between these the different entities. And the right side is a zoomed-in view of the semantic model. Here is a small example. You can see that here is the water core chiller 1. It has location in the plant room. It's another entity. And also this chiller plant, this water core chiller has a sensor point, chilled water supply temperature. This chilled water supply temperature has a temperature ID in the end side, and this ID would be stored in the temporal database. And for the AI engine part, we're using a load prediction-based child sequencing control for a test. And in this test, we predict the cooling load in the next time step, and we compare the prediction result with the threshold to make a decision for the switch on or switch off or keep the current state of the chillers. So we do the test for several days, and we choose 2 testing days for the seminar weather conditions to compare the result. And the blue line are for the reference days, which use the traditional control strategy, and the orange line are for testing days use cooling load prediction based sequencing control. And here comes the result. The left side is a conventional strategy. For the conventional strategy, you can see that the lines are for the chilled water supply and return temperature, and the stars for the on of the off state of the chillers. And we can see that in a conventional strategy, we can find that in the morning time, the chilled water supply and return temperature was really high, and this would need to bite in indoor environment condition. And in the afternoon time, we can find a frequent on and off the chillers, and this is also not good. So with the proposed strategies, you can see that the high return chilled water temperature is not short in the proposed strategy. That also we cannot see in the frequent on and off of the chillers. And we also compare of the energy consumption of the 2 testing days. The energy saving from the chillers, the chiller pumps, the cooling towers, and the total energy saving would reach to 7%. And here's come to the conclusion. Actually, this study proposed a smart data-driven building management framework for the environmental and sustainability applications. And the proposed framework comprises a semantic model integration schema and an AI engine and a smart DT platform. and it was designed to manage the building equipment and information comprehensively and interactively. And the third is we deployed this platform in this framework or platform in a chiller plant. The framework enables chiller sequence control in a robust, energy efficient manners, and achieving the energy saving range from 6 to 12%. And here are our present informations. Mr. Jamil Hall is from the building service and is a building service engineer at the electrical and mechanical service department in Hong Kong. And I'm a research associate and PhD student in the Department of Building Environment and Energy Engineering of the Hong Kong Polytechnic University. And thanks for your listening and questions.
One question myself. So
Okay.
I was just wondering, so you did some chiller sequencing and it was fully automated. So basically you were controlling everything remotely, right?
Yes, it's fully automated.
Okay, and do you have a building operator for this specific building? Or like how does it work with the acceptance of the operator? Because at the end of the day, sometimes they're a bit reluctant to do some modifications, or maybe sometimes you're gonna have some like local controls or like specific aspects that we need to take into account when we do the optimization. So do you have any comments on that?
You mean for the
For the chiller sequencing case study you just showed, because you improved the operation. So my question is more like, what did you improve? What was the control variable that you used to improve the operation? And like, how was it difficult just to go from the theoretical optimum to the implementation of the strategy you have applied?
actually at this stage, I think the we can see in here. But I think the most chiller sequence control is a relatively simple control strategy because we only needed to control the chillers to on or off, and I think the sorry, something in my mind.
Never mind. I think the optimization we need to have a try and error process because in the real application, especially a chiller plant, it depends on various factors such as occupancy number and radar information, etc. We need to have a more training to improve the models. And for your question, how about the operators in the buildings? We do have the operators because we need to ensure the plant is operate normally, reliable, while the AI application can be smoothly implemented in the building. So of course, the operators is on the site to monitor the process. And our engineer on site is also enabled to have some remote control and monitoring on the system so as to ensure the AI model and the chiller plant operations can be smooth and operate effectively. Yes.
Of course, I know this very well because we work together with Andre and Linda on this case study as well. And I think maybe we can just, and as also related to your comment, this is the ongoing work is studying the occupancy, predicting the occupancy behavior, the booking of the rooms and the volume and so on. So you can be save yet another percentage, hopefully, in the sequence. So the forecast will come in on many different aspects. And we'll also do gray box modeling with short-term integrated forecast of the weather solar release. So,
Thank you.
Thank you.
We have time for one more question. Thank you very much.
Thank you.